So, welcome back. We'll continue with our study of the kinematics of continuum mechanics. In the previous segment, we were introduced to motion, and we looked at how the body can occupy various configurations during its motion, and how those configurations themselves can be used to define mathematically what we mean by motion. Also, last time we talked about different descriptions of motion. We mentioned the fact that there are at least two different ways of looking at motion, the Lagrangian description and the Eulerian description. And the bulk of today's segment, in fact all of it, is going to be focused upon these two different descriptions of motion. Okay, so we'll start with the Lagrangian description of motion. So in the Lagrangian description of motion, what we're trying to do is follow individual material particles. So recall, we have our body occupying some configuration, the reference configuration, let's say. We have our basis, which helps us with vectors and so on, vectors and tensors. The way we're going to describe motion now is to fix our attention upon a particular particle. Let's suppose I have a particle here, right? That's a material particle. As the body goes through its motion and deforms, tumbles through space, does whatever it wants to, we are going to fix our attention upon this particle, right? And essentially watch as the body goes through its motion, and we are constantly looking at this particle, okay? When we do that, we are following a Lagrangian description of motion. Now, we also saw that talking in terms of particles is not good enough for mathematics, right? At least for the kinds of things we want to do. And the way we get around that difficulty is by observing that we can define positions, right? And those are well defined mathematically because we can talk about position vectors. In order to follow a material particle and be able to do this mathematically in a rigorous and robust fashion, we are going to look at this particle, but really parameterize all of motion by the reference position of this particle. So if this is the reference configuration, we have our basis, we're looking at this particle, we know that this particle has a reference position which we can describe through vectors once we have this basis. That is what we are going to use to parameterize the motion. Okay, so let me put that all down. So we have the Lagrangian description of motion. What this means is we will follow individual particles, right? In particular, we will parameterize our motions by the reference position of a particle. Okay, so here's the picture. We have our basis, we have the reference configuration of the body, and let's suppose that this is the particle we are interested in, right? Or rather, that's the reference position of the particle that we are interested in. Okay, so the idea is that we already know that we have the point-to-point map that defines our motion, right? Right, and this essentially tells us that the body can go on and be deformed or undergo a motion and go to a current configuration at some time t. Okay. And that will then take us to take this particle whose reference position was written as capital X. It will take it to some position in space, which is denoted by little x. Okay? Observe that when we talk about the motion here, it is indeed parameterized by the reference position, right? Okay? So So that works. So we are in a Lagrangian description of motion. But we want to go beyond this, right? Because motion, as we saw, is just, it just gives us the idea of displacement, right? Because we saw that phi of x comma t. We saw this at the end of one of the questions that was asked last time, right? We saw that phi of x comma t in general can be written as the reference position plus a displacement vector, right? So when we talk about motion, the only sort of description we have at this point when we talk about this map is that of the displacement, right, u. We want to go beyond that. In particular, we want to go on to velocities and accelerations, okay? And so recall that this u is the displacement, okay? We want to go on to the velocity, and in particular, we want to go on to something that we will call the Lagrangian or material velocity, okay? We will write it very obviously as capital V. Now, we want it to be parameterized by the reference position, right? So V is going to be parameterized by capital X and T, and it has the very obvious definition, right? It is simply the time derivative of the position, okay? That is our Lagrangian or material velocity, okay? And of course, we can go on beyond this, right? We can also talk about the Lagrangian or material acceleration, okay, which will be denoted in our lectures by A, also parameterized by reference position and time, and this is simply the derivative with respect to time of the velocity, or the second time derivative of phi, okay, right? So we have these descriptions, and they're pretty obvious, right? There's not a whole lot new here, except that we want to pay attention to the fact that things are parameterized by reference position. What we will do now is look at an example, and the example that we're going to look at is one of rigid body motion, okay? And I should mention right now that rigid body motion is a very useful idea, which we will use repeatedly in the series, in the course of the series of lectures, to elucidate very important ideas. Okay, so we have rigid body motion. I'm going to try and draw this. Well, but first let me just remind you of what this means. Reference position of the body, we're looking at motion where there is no notion of deformation, okay? And I'm saying that recognizing that I haven't really said what deformation really means, but you probably have some inkling of what we mean by things deforming. Think of distortion. We have no distortion in rigid motion, right? So in rigid body motion, this body can translate and rotate, okay? And it doesn't matter how we compose those two. We could talk of a rotation first and then a translation, or differently, right? They're going to be equivalent, and there are ways to write them so that it all looks the same. Okay, so we're talking about rigid body motion, and I'm going to try and draw this now, and I'll need to be careful because in the process of drawing this, I've got to show you a body that's not being deformed. So let's see, let me draw something easy that I can hope to reproduce. This is omega naught, okay? It's not a very good reproduction, but it is a rigid motion, okay? So let's just stick with this for now, okay? Phi of x comma t. So we want to compose it with a translation and rotation. So what we are going to do is to say that phi parameterized by reference position and time is equal to a translation, okay, where little c now is a vector depending only upon time, and a rotation. The rotation is going to be written in this manner. Q is a rotation tensor. It's one of our orthogonal tensors that we saw a few segments ago when we were talking about the change of basis. Remember, we were talking about how we could change this basis to another one, and we said that the relation between the two bases was given by the orthogonal tensor Q. Okay? So that's what we have here. Okay? And the way we will do this is to say that C, function of time, is a vector, okay, and Q, also function of time, is an orthogonal tensor, okay, satisfying Q transpose equals that tensor. But I think we mentioned in one of the earlier segments that this tensor 1 is the second order isotropic tensor. Okay, we have this, as well as, of course, we have this relation also. Q transpose Q is also equal to 1. I ought to mention that Q, we will commonly say, belongs to a particular space of tensors, a particular group of tensors that is denoted SO3. Okay, the S here is for special. O here reminds us that this is an orthogonal tensor. Okay, and the 3 reminds us that it operates on vectors in 3 dimensions. Okay, so Q belongs to SO3. When we put things together in this manner, we have a general representation for rigid body motions. Okay, and I should also probably mention here that C belonging to R3 is a translation. Okay, so this is what we have. We have this motion, and the idea is just this, right? The body can translate and rotate. Okay, so that's what we have here. Let's write out the velocity, right? So the Lagrangian velocity from here is easy. The Lagrangian or material velocity V of x comma t is partial with respect to time of phi. That's easy enough to do once we know what phi is, and this is simply c dot, remembering it's a function of t, okay, plus q dot x, okay, and q also is a function of time. Okay, that is our material velocity, and likewise we have the Lagrangian. I'll use that as short for Lagrangian, or material acceleration. Okay, A parameterized by capital X and T equals, we know that it's the second derivative of phi, the second partial derivative of phi with respect to time, and that is simply c double dot, it's a function of time only, plus q double dot, function of time, x.